Welcome back to the part 3 of the thermodynamic and heat transfer. Our today lessons is about the heat diffusion equation and the boundary initial condition. So in this part 3, we will talk about the boundary and initial condition. So to determine the temperature distribution in a medium, it is necessary to solve the appropriate form of the heat equation. However, such a solution depends on the physical conditions existing at the boundaries of the medium. If the situation is time dependent, okay, situation is time dependent on condition existing, time dependent on condition existing in the medium at some initial time. With regard to the boundary condition, there are several common possibilities. There are some possibility that are simply expressed in mathematical form. So because the heat equation, remember, the heat equation is second order. Okay, remember the heat equation is second order. We have this one, this square del square t. Okay, it means this is a second order differential equation in the spatial coordinate. So there must be a two boundary condition for each coordinate needed to describe the system. On the other hand, because the equation is first order in time, however, only one condition, termed the initial condition, must be specified. Okay, remember again, the equation is only have first order in time. Okay, however, for the spatial, it has second order equation. Now I would like to talk about the three kinds of boundary conditions that commonly encounter in heat transfer. So the conditions first are specified at the surface x equal to 0 for a one-dimensional system. And the heat transfer is always in the positive x direction with the temperature distribution, and which may be time dependent, designed as txt. Okay, so the temperature distribution, this is the temperature distribution, it may time dependent, so txt, it means the distribution temperature is the function of the position x in one dimensional and also the time. Let's talk about the first condition. So the first condition is called the constant surface temperature. So we have here is Ts. The Ts is always constant, and this is the x when x equal to 0. So it means when the distribution of the temperature at x equal to 0 at any time, okay, it means this is at any time, so it always equal to 0. So this condition is termed as a Dirichlet condition. The example of this condition is when the surface, okay, this surface has a contact with a liquid melting of the solid or a boiling of the liquid. In both cases, there is a heat transfer at the surface while the surface remains at the temperature of the phase change process. The second condition, okay, the second condition is correspond to the existence of fixed or constant heat flux. So there will be a heat flux come to the surface. Okay. The first condition of the constant surface heat flux is called the finite heat flux. Okay. So remember, this one will be equal to Ks. It means the Ks of the heat flux. Okay. So the change of the temperature will be equal with the heat flux. And then the second condition is called the adiabatic or insulated surface. In this case, since there is a insulation here, so there will be an insulation near on the surface of the object. So there will be an adiabatic when the heat cannot escape from the surrounding, okay, to the object. So the change of the temperature at the x equals 0 will be equal to 0. So it will be remain 0. There's no change. And the third condition, this condition is called the Neumann condition. And the last condition, we call it the convection surface condition. In case of the convection surface condition, there will be a convection here. So there will be a fluid that flowing, and this is the T infinite, means the temperature of the surrounding, and H is called the heat transfer coefficient. So the temperature distribution at T0 comma time, so at any time, so it here is equal to the Q of the convection. Okay, this is the heat flux of the convection. Now that's all for today's lessons. I hope you get something from this lesson, and see you next week.